Okay, we better get started. Sorry for the late start here. Of course, we're happy to have Emilian. He's been visiting all week in the FTPI. And today he's going to give us a seminar on puzzles of Gravitino production in cosmology.
So first of all, thanks a lot for invitation to be back. It's always a pleasure to be here. I'm coming very, very often since a very long time. And also because the work I'll discuss today is done partially with people which are or were here, like Keith and Marco, who was here until a couple of years ago. A common author of all this paper is Gabriele, who is there, my PhD student, who is, by the way, searching for a PhD. Excellent student. So the subject of the talk is about particle production, Gravitino, some puzzles about the Gravitino in general, and also about the Gravitino production in cosmology. As most of you know, it's not really my field, but it's something that we try to understand, and we understood only partially. Other people involved with Jan here, Marco Garcia, Sarunas, Quentin, former student who is now made the conference in Strasbourg. So this is the plan. First of all, some general reminder about spin 3/2, which is interesting history. Just remind you briefly the history. Then some of the problems that people emphasized some time ago, 5, 6, 7 years ago, to which we try to understand what is happening. Then I talk about some issues about particle production, in which we fail to understand some basic features. So somebody has ideas how to solve these puzzles, I'll be very happy to hear. So that's the plan. So let me start with some very well-known things. So as you know, in supergravity, there is so-called super Higgs mechanism, in which the helicity plus 3/2 Rarita-Schwinger field absorbs goldstino, which I'll call capital G, what follows, to form a massive gravitino. That's, of course, crucial in when we break supersymmetry. And then what will be important for today is for high energies compared to the gravitino mass, processes in which longitudinal gravitinos occur are identical to that in which you use a low energy description with goldstino, in which essentially in a low energy Lagrangian we replace the longitudinal component of the gravitino with the derivative of this spin 1/2 fermion, which is the goldstino. M3/2 is therefore the gravitino mass. So there is a long, interesting history about the consistency of such couplings of the spin 3/2 Rarita-Schwinger field, starting with this original paper. In '69, people tried to couple the Rarita-Schwinger field to U1 background, to U1 gauge field, and they really realized this could be problems, so-called Veros-Wanziger problems, some potential acausal propagation. Then when supergravity was invented in '76, this was one of the first questions.
Sorry, question. Charged, just a general spin 3/2 particle, or
yes.
What do you mean charged gravitino?
Well, yeah, it's not charged gravitino.
It's
Charged spin 3/2.
Okay.
Charged spin 3/2 particle. Yeah. When supergravity was invented in '76, this was one of the first issues which arise. Is the gravitino supergravity has the same kind of problems which was pointing out a long time ago by Veros-Wanziger, and Deser-Zumino proved that the gravitino propagation in the first models of supergravity was causal, and then much later, Deser-Waldron proved that in the cases in which gravitino supergravities are charged, these are called gauge supergravities. Again, there is no problem. So in all explicit supergravity models, there was no problem, no causality of the fact that it was of the type which was originally pointed out. Now, history is therefore strongly suggests that the usual supergravities have no problem. However, there is another version of supergravity which will play an important role in the first part of my talk, in which so the usual supergravity, supersymmetry, of course, we have the same number of bosons and fermions, but then there is so-called nonlinear supersymmetry realizations, which in number of bosons and fermions are different, in particular the original first, well, or the second supersymmetry models in 4 dimensions by Bogolyubov, which was of this type. Beautiful paper. And such models, nonlinearizations can be constructed in supergravity, and they were used over the last 10 years to construct simpler models of inflation in supergravity. So these are nonlinear supergravity models, not the usual one. And in particular, it's possible why you would like to do this supergravity, just to minimize the number of fields. To do inflation supergravity, typically you need at least 2 or 3 pairs of fields, a lot of scalar fields in particular, whereas you'd like to have just the inflaton if possible, massive gravitino, graviton, nothing else. So such models with such spectrum do exist in supergravity, but in nonlinear realizations, and this is one example to be concrete. First of all, you can realize nonlinear supersymmetry. You can write even the original Volkov-Vakulov Lagrangian in the standard superfield formalism, Besson-Butler like in the book, if you want, in which you impose a constraint on a superfield, and that's the expansion of the superfield in this superspace parameter theta, in which this is the goldstino. There's an auxiliary field, and usually have a scalar field in the partner of the goldstino. If you impose this constraint, there is no scalar anymore. It's just a bilinear in goldstinos. So this was proposed by Rocek, and it was shown immediately that you can write Volkov-Vakulov Lagrangians in a very simple way. It's essentially Polony-like Lagrangian with a linear superpotential, which is precisely giving the Volkov-Vakulov non-linearly supersymmetric Lagrangian. A refined version of it is having a second multiplet, let me call it inflaton multiplet, in addition to this goldstino multiplet. So let me call this as a goldstino multiplet because it contains the goldstino terminal supersymmetry breaking, and impose a second constraint of this type in superspace language. This constraint eliminates, so this constraint eliminates the scalar here, part of the goldstino, and this constraint eliminates half of the degrees of freedom of this complex scalar, the corresponding fermion, which is the inflatino, and even the auxiliary field here is not determined by the usual supersymmetry algebraic conditions, but is determined by the constraint itself. So in the end, you will find as the degree of freedom only a real scalar, which can be the inflaton, and the goldstino, which becomes partner of the gravitino, if you want. So these models have minimal degrees of freedom of supergravity, just the graviton, massive gravitino, and a real scalar, which is the inflaton. So you can use the usual superfield approach. You can write a scalar potential, superpotential. Despite this, the degrees of freedom are just the minimal one you would like to use to do inflation.
Does a linear realization of this exist? Like if you went to high energy and you identified
I'll talk about this. So ideally, what you would like to do is the following: to start from a standard supergravity Lagrangian and then decouple heavy particles. For example, to decouple the partner, the scalar partner of the inflaton, to decouple the inflatino. This can be done, but this constraint has another feature, which it turns out to be unphysical, and this will create problems. The fact that it determines also this auxiliary field, and this create problems. But if you want to just to decouple the imaginary part of this and the inflaton, you can do it. Essentially, you have to do something which is adding high-dimensional operators, mass terms. It can be done, but it turns out, and I'll not discuss this in detail, when you try to eliminate this field, there is something which is happening, and this is the origin of the problem that we'll see later on. I'll not discuss this in detail.
But isn't that weird that there's no linear realization?
It is. And that's precisely the reason so for me, this constraint is problematic. In other words, it's not free. There is no free lunch. The first constraint, for example, can be realized in the way you say, just give a large mass to the scalar, and in the infrared you get.
But there's still the question, where do you get that large mass from?
Yeah, for me, even in this case, it's not very satisfactory physically, but you can put some operator to put a large mass for the scalar.
It's not so obvious because
It's not, but in this case, you know probably the story. I can write the Lagrangian. To me, is not satisfactory for a reason we don't need to discuss here because it will get us too far away. You know the story.
yeah, if you do that,
Yes,
sure.
yes. If you do this, this gives a mass to the scalars goldstino. In the infrared, you get this.
Yeah,
If you ask me if I'm satisfied with this, my answer is no. But okay, you can do it. But if you want to,
I'm laughing is because, you know, what we do is add the quartic term, right? And you say, no, you can't do that. You can do this. But now you're telling me to do this, you have to do that. So that's.
well, if
No,
you
but
want
wait, is that linearly realized there?
here, yes,
Yes.
Yeah,
right.
yeah,
that's
Yeah,
fine. That's standard.
yeah.
That's quite normal.
Yeah, well, it's quite normal, other than that you have to explain why you're getting a quartic term there, for example. Right? You're putting a non-normal.
That's why I'm not completely satisfied.
I know that's why. I
Yes,
understand,
but
but
the
there's
strength
nothing.
amounts to another different kind of question that has to be
Yes.
answered as well.
Yes. So,
You're just moving it's just moving the problem
Yeah.
from one place to the other.
but you know, this could be one. Actually, I can give you other examples. So this is just one example. Well, okay, this is not the subject that I talk. I know three examples which are just a nonlinear realization to start with. So I know how to do this. However, this is different. If I,
Yeah, that one's different.
this one is different, you know very well. If I want to do something similar like here, I have to add higher derivatives operators to start with. And higher derivatives are can be problematic. I don't discuss this today, but
Would they be problematic because they would lead to propagating auxiliary fields?
yes. In this case, as far as I know, there are no. These are interactions containing higher derivatives. So it's not really, you are not really modifying the propagator to have additional degrees of freedom. However,
You add some additional higher derivatives.
Yes.
In terms of the Taylor
But
differential.
yeah, but which are interactions if you want. So you don't necessarily modify the number of degrees of freedom, the original number of degrees of freedom.
Yes, but you could lead to equations of motion where the auxiliary fields are dynamical.
I think this is not the problem. I don't think it happens here. However, what it happens is that the higher derivative operators, even if you don't modify the number of degrees of freedom, have some constraints like positivity constraints, things like that. And this will be one of the problems which arise in this case. You have to add higher derivative operators, and I'll show you explicitly you can generate some additional constraints.
This trick can only be applied to the goldstino.
Which one?
S squared equals to 0.
Well, you need Fs to be different from 0. So this is a field which breaks supersymmetry. Yeah, you apply it to the object which breaks supersymmetry. Yeah. This you apply to something else, which
Right.
has nothing to do with supersymmetry breaking, and there are other kinds of constraints you can do that. A lot of the constraints are of these types. That's fine, but in my opinion, this one has a problem. In my opinion. And unfortunately, it's precisely this one which leads to this minimum model certification.
No, you don't need that constraint for, minimal in terms of.
In this sense of non-linearization, in this sense. Well, no, I give an alternative. We propose an alternative.
No, but you don't have to reduce the number of fields. Right?
No, but I'll argue later on that I have alternative in which I eliminate the scalar partner of the inflaton. I eliminate the inflatino. I don't touch this object. I leave it like in the usual supersymmetry case. And then
But you don't have to
I
eliminate
know, but let me finish. And if I do this, if I just don't touch this object, so this is a different constraint, all the problems that we see later on just disappear. That's what we did in this paper with Gabriele and my colleague. So there is an alternative with the same degrees of physical degrees of freedom, minimal model equation, which have no problem whatsoever. You just have to modify this in a certain way.
Sorry, is there any easy way to see the first term and kill the potential real?
B is this object here. Yeah, it is real. H is a real function. And these are super fields, if you want. So this is phi plus phi bar over 2. This is phi minus phi bar over 2i. This is real by construction. H is a real function, yeah.
Yeah, B is real.
A and B are real, yeah. Yeah, superfields, yeah. Okay. Now, something which will appear later on in the discussion is the sound speed in supergravity, which is defined through the, we'll be interested later on in sound speed of the gravitino, because this will be one of the problems which will appear, as you'll see later on. It's defined through this special relation, frequency versus space momentum. A is a scale factor, so I'm in a FFW-like background. And if you do this for the spin 3/2, the transverse component has a standard dispersive relation with the sound speed equal to 1. And for the longitudinal components, it can happen two things. First of all, the sound speed is less than 1. That's not unusual. In the cosmological background, this object can propagate with a sound speed which is less than 1. That's fine. But there were two problems that were mentioned in literature. One of them is that when the sound speed goes to 0, this is a problem already because the frequency doesn't depend anymore on the momentum. And then there is a second problem that we encountered in our paper with this Jan and Sarunas, in which we even in some examples given by Kolb and collaborators earlier on, the sound speed can be larger than 1. The sound speed larger than 1 is just an inconsistency of the theory. The theory is just inconsistent. So the question is, how is it possible that this will be inconsistent? If it's supposed to be supergravity, how is it possible?
Well, so the usual problems with inconsistency is when you take omega to infinity and your sound speed, if it goes back to 1, then it's okay. Right?
Well,
is this a function, or is
this?
Yeah.
No, it's
just a number?
It's a function of time. So it depends on time. And so it depends on the inflation trajectory where you are, but in some points on the trajectory, it becomes larger than 1, and that's problematic. And I'll show you that this is related to some inconsistency in the effective Lagrangian, which means that that constraint has a problem in itself, because this is not possible to get from a consistent initial theory. Yeah, okay. So normally this sound speed is between 0 and 1, and there are two problems which were mentioned in literature. One, which was discussed in this paper, common collaborators, and actually it was an earlier paper by Hasegawa, Terada, and other people, in which sound speed can become 0 at particular points on the inflation trajectory. And it was discussed later on by common collaborators, and then they realized that in this case, if you do a standard computation of the number of longitudinal gravitino produced, then the helicity 3/2, there is no problem. Helicity 1/2, the longitudinal gravitino, the number of particles increases with the momentum, and there is what they call catastrophic production. So there is no decrease for large momentum in the number of produced particles. So that's called catastrophic production.
So minus in some other language, if I rescale the speed of sound, it's if it goes to 0, like if I rescale it, then somewhere it has to pop up as infinitely strong coupling or something like that.
Yes. So I learned that this one is an issue of strong coupling.
Right.
which in my opinion just means that the effective theory breaks down, is not necessarily inconsistency in the theory, but something is happening there. Yeah, I'll.
Emilian, usually when it was this kind of stuff of longitudinal polarization, for example, for vector particle, the leading term was cancelled because of conservation of the current, the most singular term. And I was guessing that here the leading term would be also kind of interaction with energy momentum tensor, or what would be the leading term, you know, what is the conservation law associated with this 3/2 particle?
Yeah, is the supercurrent.
Right. But if you if you do not have conservation, then you have an anomalous, you know, growth of the amplitude, right? Because normally, you know, take just a normal, let's say, massive photon, for example. Okay, longitudinal polarization would be also growing if the current is not conserved.
But for a Proca field,
Like field as well. So it's crucial that the current is conserved, because then the leading term, the most singular term, goes away, and then only the next term would show up. You see, so that's why I'm wondering here in your example, where the leading term is kind of analog of, say, look, you're right that it's like a conservation of supercurrent, right? But if it's kind of no conservation, then that indeed a longitudinal polarization or whatever helicity 1/2 would be growing up as 1 over power of m, right?
but so this is not. I don't know if there is any connection with the usual amplitude which grows with energy. Maybe.
No. But you wrote. Remember, you wrote this expression. It is p mu divided by m multiplied by epsilon alpha. You know, remember, is in the very beginning, right? When it was kind of kinematical stuff you discussed at the beginning, when you had this, here, right?
Yes.
And this term p mu divided by m 3/2, it is the one we are talking about.
Yes. Well,
right. Yeah. And if you do not have mechanism to get rid of this term, that indeed it would be kind of, you know, growing with, consider the case where m 3/2 is small, right? Then it would be catastrophic, right?
I don't think it's so simple. I mean, I don't see the connection between this and the sound speed, because the problem appears only when this dispersion relation it becomes independent of momentum. So to me, slightly something else, but maybe I'm wrong.
No, but still, you have this singularity 1 over m, right?
Yes. Yes.
And to get rid of this singularity, you do need some kind of conservation, right? Like d mu acting on this source would give you 0, then this term would disappear. And maybe, I'm not sure, maybe it's related to this velocity of sound. You see, not directly.
Okay, let's discuss it at the very end. Right now, I don't know.
Okay, I'm sorry.
No problem, Arkady. Thank you. I think we are here. So here. Okay, so there is this rays, in which means that the total number of gravitino produced in this particular point in which the sound spin becomes 0 becomes unbounded. And again, I agree that this is a problem of strong coupling. So it's not necessarily inconsistency, it's a problem of strong coupling. So this happens actually in the this minimal models of inflation based on this, what I call orthogonal constraints, at points where the inflaton kinetic energy becomes equal to the SUSY breaking scale, and in the cases where gravitino mass is a constant. Okay, as I learned later on, without really many details, indeed, this is a problem of strong coupling, which arises precisely when your inflaton kinetic energy becomes very, very high, because this is somehow related to the cutoff of the theory, indeed. But there is a second problem that, again, the one which we discussed in even our first paper with Kisarunas and Yan, is that you can have even sound speed which becomes larger than 1. And this is a causal behavior. This is not an ultraviolet problem. So this one, I'll argue that this sound speed equal to 0. In some sense, it's an ultraviolet problem in which if you go to the ultraviolet, maybe your theory, you have to change your theory maybe. This one is not an ultraviolet problem. It's a problem which even for a very low momenta, you have a big problem, you just break causality. So this is really an inconsistency. So the question is, how do you solve this? If it's not an ultraviolet problem, you should be able to understand it even at low energy with goldstino lagrangians. We can forget supergravity, go into low energy limit in which the longitudinal component, which is the main problem here, is described by the goldstino, and the goldstino lagrangian should feature something which understands that can have a problem. So that's what we understood in this paper, I believe. So before we understood with Dalagat and Ferrakos that this kind of constraint needs higher derivatives, which could by themselves be problematic, but here we were a bit more precise to see what's the real problem. So, and both problems for 0 sound speed and larger than 1 appear in this nonlinearization supersymmetry. They don't arise in standard supergravity. They are relevant for phenomenology and cosmology. In particular, they are used in this, as I said, the simplest model of inflation. So,
Sorry, but can you go back to the plot? Sorry, just to understand the problem. Can you go back to the plot? Yes. Is your problem to see the non-vanishing abundance of the Gravitino on superhorizon scale or subhorizon scale?
If you really integrate to find the total number of helicity 1/2, you find infinite if you want.
The problem is to see the absence of non-vanishing NK at superhorizon scale.
Yes. So it should go down.
The right part is usual. That's unusual.
This one is fine. This one is unusual.
That one is unusual.
Yeah.
So that corresponds to the subhorizon at the end of inflation.
You would expect, I think, for very large momenta, you would expect.
It diverges. So the problem is that you get a divergence.
Okay, that part is problem.
This one. Yeah.
And that's the population on subhorizon scale at the end of inflation.
Yeah.
K is larger than AEH.
Yes. Usually you find a suppression, no? For large momenta, very large momenta. Okay, now before going to this goldstino lagrangians, you can just compute the sound speed in supergravity. And then you find an expression which is like this. So if you remember, I wrote for you this Lagrangian here. So if you impose orthogonal constraint, we wrote this effective Lagrangian, which we had these functions f, g, and this function here, h. And you'd expect to find the causal theory for any function h, f, and g. You would expect to find the causal theory for any possible functions. And if you compute in supergravity the sound speed, you'll find this expression here, in which this parenthesis has to be positive in order to avoid the causality problems. To avoid to be causal, you need a condition on these functions here. And to me, this seems strange that you have to constrain these functions in the supergravity theory such to find the causal theory. Some people said, like the Carlos Schlim, they say, fine, you just choose the function such that this is satisfied and that's it. In my opinion, it should work for any possible functions if the theory is really a decent, maybe it's debatable, but we try to provide understanding why this can happen and how you can avoid to find something causal for any kind of functions.
But if this condition is broken, doesn't imply that then it's like kind of analog of, say, negative m square, right? That the theory would be unstable, when it's broken.
No, it's really a breaking of causality. you have
No, right, but causality breaking if this you are in a unstable situation where you see you have
you're right. But I learned that you can see it as the sign of a certain higher dimension operator, which by usual analytic constraints should have a given sign, like d5 power 4. Remember, the sign in front of d5 power 4 has to have a certain sign, positive, I think. Here I'll show that the sign, this condition can also be understood in the same way as a certain operator, which also the coefficient should be a given sign.
No, but then it's similar to what I suggested, like negative m squared, right?
Yes. Absolutely. Yeah. You are not in the correct ground state. Yeah. Right. Okay, so let's try to understand a bit better this causality problem. So we start in supergravity with the gravitino, which has a transverse component and the longitudinal component, which is essentially the gamma trace of psi, and this this inflaton. Now, in what follows, in the next 5 minutes, I'll use the goldstino lagrangians, which are the rigid version. So you take the n Planck to infinity, you find the low energy Lagrangian containing only the goldstino and the inflaton, and I claim that I will understand exactly, I'll get exactly the same condition on the that I found before. Is this low energy Lagrangian? In other words, the n Planck didn't play any role in the story. Fine. So if you work out the goldstino Lagrangian, that's one of the works that Gabriele worked out in detail. A is what I called phi before. A is this inflaton. This is the low energy goldstino Lagrangian. It's a complicated Lagrangian depending on this function f, g, and h. And then what is important is that after a certain number of Fourier definitions, you'll find an operator of this type, a high dimension operator containing two derivatives of the scalar. This goldstino kinetic term, like you multiply the two, and there is a positivity constraint from dispersion relation arguments, which tells you that this coefficient here has to be positive. That's precisely the analog of this d5 to the 4. It's exactly the same kind of argument. So this is a rigid supersymmetric Lagrangian, and you find exactly the same condition that you find in the full supergravity that we derived in our paper. And actually, if you work out the sound speed completely from this Lagrangian, you find exactly the same expression, actually. So we found the same expression for the sound speed from supergravity. So the causality is just like in these original papers by what was Nima, Kanyamed, Tratazzi, and the others. The same kind of arguments tell you that you can use, in this case, goldstino Lagrangians, and in this case, you find exactly the same result in supergravity. So this was a consistency problem, a consistency condition. Now the question is, what was wrong in the original supergravity Lagrangian? If you violate this, what was wrong in this original supergravity Lagrangian? Was it a standard supergravity or not? Now it turns out, and I don't have time to explain here, the original condition we imposed there in order to eliminate the scalar, the fermion, and the auxiliary field are actually a sum. It's a kind of a reducible constraint, which you can write it as 3 different conditions. And the problem comes from this one here. This one means that you need to eliminate a scalar. You can essentially add a very large mass term. It can be done without even derivatives. This one, you have to eliminate a fermion. It can be done also in a relatively normal way. This one, personally, I don't know what it means. I don't know what it means to eliminate an auxiliary field, if you want. And what we did is the following. We construct Lagrangians which impose just these two constraints, and we reworked again the sound speed. In this case, the sound speed was always less than 1, always. In other words, what was wrong in this orthogonal constraint is that you are imposing a condition which is unphysical. when you impose a constraint to eliminate some fields, this should come from some physical input, from some physical mechanism to decouple these fields. So it's not these particles. It's not just do whatever you want and everything is always consistent, in my opinion. That's my opinion. So we provided these alternative models. And actually, in this case, again, there's absolutely no causality problem. The sound speed is always less than 1. However, this sound speed equal to 0 can still arise in this case. You can still get sound speed equal to 0, which, as I said, it's an ultraviolet problem. And you have to change maybe something in your theory.
So minus for those of us who completely forgot everything about supersymmetry. So because if I just take the usual, like the simplest case, I would just get Hughes auxiliary field, find the equations of motion.
Yes.
And then just
Absolutely.
it gets eliminated by itself on the equation
Absolutely.
of motion.
Absolutely.
Right?
Absolutely.
So I can possibly apply the same logic here, right?
Yes.
And
And that's precisely I'm proposing. I'm proposing this eliminates a
that's
scalar.
physical, right?
This eliminates a scalar. This eliminates a fermion, and you just don't touch the auxiliary field, and everything will be fine. In this case, you don't find any causality problem.
Yeah, but it's in some sense, the two conditions are incompatible, right? One's from the equation of motion, then you're imposing another one, right? But that's what it would be like.
Not really. Not really, because if the auxiliary field is just determined by the constraint, you don't have anything
No,
to.
but aren't you imposing a third condition where you have the problem?
Our proposal is not to impose a third
I-
condition.
But I'm saying.
Before, yeah.
Yeah.
That's what
why
people
there's
are
a
doing.
problem,
Yeah.
right?
Yeah.
You have two conditions there, right?
I don't think you need to see it like that. I mean, the auxiliary field is determined. You have a certain algebraic expression given by this. You just plug it in Lagrangian and that's it. Naively, you say it's fine, but in my opinion, it's not okay. It's not okay. It doesn't correspond to any physical decoupling, and therefore you can get a causal theory. And that's precisely what's happening.
And the origin of these constraints?
This one?
No, any of them.
This one, you just add some higher dimension operator. I forgot. I can show in our paper. This is also another high dimension operator. And this one is a very funny higher derivative operator. It's very funny higher derivative operator, which at first, just looking at it, I couldn't tell you if it's fine or not fine. But this one, I think, just looking at the corresponding operator, I wouldn't say why it's completely funny. So probably the original higher derivative operator which you have to add here is problematic in itself, but I don't think we understood exactly from the very beginning what was wrong about this higher derivative operator here. Was not clear, but probably something wrong with it from the very beginning. Anyway, if you don't impose this, the sound speed is less than 1 for any functions in your theory.
So there is a higher dimensional operator that you can add
Yes.
to impose a certain condition.
Yes,
Seems
there is.
to be fine, but,
So there is a one.
what's the form of that operator? Take a look.
I don't have it here. I can show you. We can discuss it later on. It's,
There's no obvious meaning of that.
you can ask yourself, okay, so what should probably happen is that the higher dimension operators that lead to this and this probably can be obtained by really integrating out some even higher degrees of freedom, probably. So probably higher dimension operators, you can get them explicitly. This one, the one which you need here, probably you cannot get in any sensible way, probably. I guess so. Okay. Now, I don't have much time, I think.
No, we started late.
Okay. Okay, now, of course, now about when can you use the low-energy goldstino actions and when you can use, when you cannot use it. That's the analog of the equivalence theorem, I think, for cosmology. You need these two conditions now. And then this gamma trace, which is the longitudinal component of Gravitino, goes into this goldstino law. So this is just the cosmological version of the equivalence theory for goldstino. I showed you that we could understand this causality problem uses the goldstino action, I now go to things which we don't understand. I'll show you two puzzles we have for the gravitino. One of them will be that these low energy goldstino actions, we believe that you cannot use these low energy goldstino actions to really talk about the gravitino production, at least the energy in the gravitino, for reasons which so starting from now, there are things which we have some puzzles.
Yeah, Emilian, in this point, I would say that kind of testing signal is that whether it's possible to go to the limit where goldstino has a zero mass. If the theory with zero mass exists and you have a limit of zero mass, then it means that then at certain scale it would be no problem, right? But in what you presented, it's not clear where.
I think there is no limit. I think there is no limit. The limit, I think, is not smooth. I think.
Yeah, right. But then it's
actually you can see it maybe here. Maybe you can see it here. Maybe no.
Yeah.
Not. I think there is no limit. So anyway.
No, but it is what I tried to discuss before, right? Because when there is eventually kind of conservation of supercurrent or whatever at certain energy, then the limit would exist, right? But if there is no this kind of restoration of supersymmetry, then indeed limit doesn't exist, and then there is no wonder that it could be indeed problem. I agree.
Okay. Yeah, maybe you can understand it like this. Absolutely, yeah.
So there are three different types of high-dimensional operator that gives you these three informational conditions, and all of them respect supersymmetry and existing gauge symmetry in your model. But by hand, you remove one of those types, which gives you the third condition.
Yes.
By hand,
Yes. Well, it's consistent because these three. So the original.
I understand phenomenological motivation for that.
No. I mean, the original superfield constraint people are using can be literally decomposed into three different ones. And you can really remove any one of the three you want.
Or because they're independent.
They're independent.
They're independent.
Yeah, they're independent.
So it's not abundant. Presence of those three different kind of high-dimensional operators. It's not redundant.
They're not tied together. This is
how could you remove by hand?
Sorry?
How could you remove one of those?
Each operator has a different coefficient, which are completely arbitrary. Each of them are separated supersymmetric if you want. You just set one coefficient to 0.
Yeah, you can do that. But
yes.
Because all of them just respect the symmetries of the theory.
Yes.
You do that by hand.
Yeah.
Okay. Yeah. You do it by hand.
Yeah.
But also the problematic constraint is imposed by hand in the beginning. So it's just another theory. You start from a different starting point.
Yeah, it's a different starting point. Yeah.
Okay.
Yeah.
Improved version of what.
It's a different microscopic theory. Yeah.
Yes, and I think the answer to my question might be on this screen, because when you go to the goldstino limit and you decouple M-Planck, is there a four fermion operator?
A lot of them.
Be a scale there.
Yes.
The scale is this group there.
Yeah. Yes. And the cutoff of the theory in this Lagrangians is not M-Planck.
Exactly.
It's related to this F. And actually turns out that if you look specifically of this hard derivative operator that I wrote, you realize when the sound speed goes to 0, you realize there is a strong coupling problem. So there is some operator which indeed the operators, the coefficients become large, indeed. So this is the origin of this problem. But that's probably a UV problem.
But do you know actually simple solutions, probably just to add a scale? I mean, to add the original.
Yeah.
The original fields probably fixes it up.
Yes. Yeah. You don't get these problems in the standard models with linear realizations. Yeah. Okay, so but the origin of this catastrophic production was precisely this CS goes to 0. So that's it's a highly UV sensitive, and therefore it's not clear that this problem is really a real problem, this catastrophic production. But here I'll still try to, yeah. Here I'll have another viewpoint here.
Which means remove the constraint.
Here I'll take another viewpoint, which is the following. Is the flow that I showed you really sensible, even forgetting about this? Is this number of Gravitino something which is related in any way to production during inflation or not? And in my opinion, there is a problem there. And since anyway, I don't have much time, I'll maybe go directly to the Gravitino.
You still have at least 10-15 minutes. Yeah, you started at 40-45, so you still have at least 15 minutes.
So let me then remind you a little. So let me start then with the simplest example, which is the Broca field, especially since Broca was Romanian. So it's very similar to the Gravitino. You have a gauge field which absorbs the goldstino boson to becomes a massive gauge field. There is a transverse and longitudinal component, and we can also talk about production of. And these are the people which worked out this. We can also talk about the production of gauge fields during, let's say, inflation or cosmological evolution. There is again an equivalence theorem here, no, in which processes with longitudinal helices of gauge fields are described by goldstino bosons. So it's very similar to the Gravitino, but the situation here is well understood. And so we have transverse and longitudinal components. We are discussing time dependence, something like an FFW metric, and the transverse and the longitudinal component of the gauge field satisfy different equations. In particular, as you see, for the transverse component, the sound speed is 1. The sound speed is the coefficient in front of this k squared, and there is no problem. Whereas in the case of the longitudinal component, the dispersion relation is more complicated. It's more complicated if it involves the derivative of the scale factor. It's more complicated. So here you can decompose the gauge field into, again, transverse component and the longitudinal component, which is defined like that. And something which will be very important is that when people quantize the gauge field during inflation, you are always using this time-dependent rescalings going from this longitudinal component to something which is canonically normalized. So this is time-dependent, and this will be a source of problems, which to a large extent, I believe, are known. So this factor here is time-dependent. So when you write when you quantize the field, introduce the creation and annihilation operators, you are doing it for this canonically normalized field, no? And then there are two objects you can construct. One of them is the Hamiltonian of this canonically normalized field. This I'll call it instantaneous Hamiltonian. And everybody is quantizing Hamiltonian, the instantaneous Hamiltonian. We talk about particle production for this object, and we can diagonalize it. And this is the diagonal form of this instantaneous Hamiltonian with this frequency that you saw before. And these creation and annihilation operators are the original ones in the quantization of this longitudinal component modulo Bogolyubov transformation. Because they are related to the original creation and annihilation operators through Bogolyubov transformation. And you say that if you take, let's say, the Bunch-Davies vacuum, which is annihilated by the original annihilation operator, you'll compute the expectation value of this object in this vacuum. You get the number of particles produced. This is the number of particles you produce. That's the usual story.
Emilian, but when you did this normalization, it looks like it's you are losing locality, right? Because it's divided by k, right? For example, for small k, it's singular factor, right? So it means that your canonical normalization associated with original expression was a local theory. now effectively it's non-local, right? If you like, when you divide it.
Yeah, it's non-local. It's non-local. Yeah.
Yeah. No, okay. So sorry. So is in this sense, it's no kind of, but it's related then to the problem with speed, what is the speed or whatever? Because if it's non-local object, right, then you know, it's kind of you're collecting from large distances, I mean, not from short distances at small k.
Yeah. Yeah.
I'm not sure. No, but maybe
I don't
you
know if
can
it's a
say also.
problem.
You don't think that. Okay, sorry. Okay, so maybe.
I don't know if this is a problem. In the case of gauge field, I don't think it's any problem. I'm sorry?
No, it's only a not.
Omega naught is
What was that?
this frequency, the standard frequency in the FRW background.
So it's a constant, 0.
No, it's not constant because it depends on time. Yeah. Okay, on the other hand, you can compute the energy momentum tensor and compute the energy as the T00 component of the energy momentum tensor, and then you find you can also diagonalize this object, and your diagonalization of this is different compared to this instantaneous Hamiltonian. There's a diagonal form. These creation and equation operators are related through a different Bogolyubov transformation compared to the usual ones. So this energy operator and instantaneous Hamiltonian are different. And what it's simple to realize is that the two are related through a Bogolyubov transformation. So this Fock space of the energy operator and the Fock space of the Hamiltonian, if you want, instantaneous Hamiltonian, are related to a Bogolyubov transformation that you can write explicitly, analytically, in a very simple way. And the two Fock spaces coincide only in the large momentum limit. Only if you have very, very high momenta, then the two Fock spaces indeed align to each other, which means that in general, they are not the same. In particular, the Bunch-Davies vacuum, which is the ground state of the instantaneous Hamiltonian that people use to compute particle production, is not the state of minimum energy. So if you compute the energy of the Bunch-Davies vacuum, you'll find a result which is not just the ground state, or just not the ground state, but you have an energy which is different from zero, and actually you have even to renormalize it because you have UV divergences, which means, which is not really a big scoop, is well known, the number of particles is not related in a simple way to the energy. So the energy produced during cosmological evolution is not equal to the number of particles computed from this instantaneous Hamiltonian times the frequency. It's something else. To finish the story of the gauge fields, the longitudinal gauge modes are produced much more importantly than the transverse modes. They are produced even in the massless limit, so there is an enhancement of this production of the longitudinal modes compared to the transverse modes. And fine, and here I took a plot from one of these papers in which you see a production of the longitudinal modes. In this paper, this gauge field, Procca gauge field, was dark matter candidates, and they had a plot of the power spectrum, which was for a very large momenta was similar to a scalar field, and for a low momenta they had a different behavior. So the longitudinal component behaves like a scalar field for high momenta and behaves differently for low momenta.
But was there a Higgs mode, a radial mode there as well? Or not?
Sorry?
Was there a radial mode?
No, no. They just took a Procca Lagrangian in an expanding background and they worked with it. Yeah, if you put a radial mode, you expect again some changes in the ultraviolet. Yeah.
Well, I expected.
Yes.
Finite.
Well, yeah. I don't know. So they did really Procca field. Yeah. Yeah.
Because that one has a unitarity cutoff, right?
Yes. Procca Lagrangian has a unitarity. Yeah. Yes. Yeah. Procca has a cutoff. Yes. Probably was not important for them because most of the production was done here, and maybe it's fine. They don't discuss it, but I expect it could be fine, could be reliable. For the Gravitino production, we have tried to do the same. We decompose the Gravitino in supergravity into a transverse component, into a longitudinal component. Again, you have to perform, in the case of the longitudinal component, a time-dependent rescaling to bring it to the canonical form. Every time you are doing a rescaling in which the prefactor is time-dependent, the rescaling is time-dependent, there is something which is easy to understand. The Hamiltonian of this canonically normalized field, which is this instantaneous Hamiltonian, is not the same compared to T00, which is the real energy operator. That's something which is logical, if you want, is well known. Essentially because you are doing, you take an equation like this, a time evolution. If you do a rescaling which is time dependent, it is obvious that your Hamiltonian changes, not just, it's obvious, yeah. And indeed, they are different. So, so that's the instantaneous Hamiltonian of the longitudinal Gravitino. Instantaneous Hamiltonian, again, is the one in which you rescale the field to make it canonically normalized. You compute the Hamiltonian in the usual way. This is not the T00, your energy, which appears in the Einstein equation. It is not. The transverse one has no problems. The transverse Gravitino has no problems. When you quantize this instantaneous Hamiltonian, indeed you find the Hamiltonian in which in the dispersion relation, you have the sound speed, which can go to 0 for some points in the inflation trajectory, which was generating this catastrophic production. But this was by using this Hamiltonian here. So formally, the number of Gravitino you produce can become unbounded because you are computing starting from this instantaneous Hamiltonian. However, if you take really the T00, which is a real energy operator, what you find, it's a different for space. This is diagonal form of this T00, if you want. And in this frequency appearing here, the coefficient is not this sound speed, it's something else. And this something else never becomes 0. So we believe that if you compute, and actually we didn't do it for reasons, we just didn't do it, if you want, until the very end. It turns out that there is no reason to believe that the energy stored in the production of Gravitinos becomes unbounded in any way, because there is nothing here which goes to 0 in this dispersion relation. So we expect that the energy you produce will be completely finite, and there should be no problem. Okay, let me go to the almost to the end. One of the results of our paper, okay, it's just a computation, but we didn't find it elsewhere in the literature. It was a full computation of the energy momentum tensor of the spin 3/2 Rarita-Schwinger in curved space-time, which was worked out by Gabriele, that is needed, and there are various checks that is consistent. We are planning later on to really use it to do a full real computation of this energy produced starting from a certain, let's say, Bunch-Davis vacuum state, if you want, and find the energy produced. We didn't yet do it. And we have a puzzle. We have a first puzzle, which I maybe not mention. We have another puzzle, but which is the following thing. I don't know if it's a real puzzle. I told you how to find instantaneous Hamiltonian for longitudinal Gravitino. You just take the supergravity Lagrangian, you canonically normalize, you find this Hamiltonian. If you take the low energy goldstino action, you compute the T00, the usual energy operator, you find the same object. But these objects are not the real T00 of the original Rarita-Schwinger, in which you project on the longitudinal Gravitino. So the original energy operator from the Rarita-Schwinger action of the longitudinally polarized Gravitino is not equal to the energy operator in the low energy goldstino Lagrangian. Even if we proved the equivalence theorem, That's something that personally I don't understand. And this one was equal to this instantaneous Hamiltonian of the longitudinal gravitino. So in my opinion, you cannot use low energy goldstino actions to discuss gravitino production. I don't understand this result. So again, the conclusion is that this low energy goldstino lagrangians do not capture the correct energy of the longitudinal gravitino. This may be obvious for some people, but not for me. So conclusions.
Look, but I don't. Once you wrote what you believe could be low energy effective theory, you can kind of use this low energy effective theory as a way to calculate your energy momentum, right? From this effective theory, right? Then it would be energy momentum defined not by original energy momentum, but the one given by your effective theory.
You see, no, I understand that. That's why I call it a puzzle. It should work. We checked, rechecked, and rechecked the result, and we are relatively convinced that we didn't do any mistake, but we don't understand the result. I agree with you. I agree. I don't understand personally. But we rechecked the result a lot of times. I don't know. It's a puzzle. Yeah.
Okay.
We checked that this energy momentum tensor here is conserved. Gabriele computed in 3 different ways. We checked the conservation for an arbitrary curved background. So we don't understand why this T00 is not the same as the one given by the goldstino low energy actions. Personally, I don't understand. It's true. There should be a solution, but we don't know it. So these are the conclusions. So there should be a solution to this puzzle. So I believe that the equivalence theorem should work indeed. It's important to discuss particle production for gauge bosons and gravitinos indeed. The causality constraints, I think we understood them very well. These are positivity constraints, as they can be understood both in supergravity and in the goldstino lagrangians. We can construct models of inflation with no causality problem whatsoever by modification of these constraints. And then the last part, which is things which we are not sure of everything. So the gravitino production does not seem to be accurately captured by goldstino actions. There are these UV sensitive effects. It's a bit strange indeed that the goldstino action does not capture correctly the energy of the longitudinal gravitino, but we don't have a solution to this. So the back reaction, again, I'm just repeating, back reaction of gravitino production looks different in supergravity in these low energy goldstino actions. Technically speaking, it's related to these time-dependent theory definitions. But this is not a physical answer, so I'm not sure if, yeah. And why would be interested in all this? Well, because we would be interested in gravitino production when you have very heavy superpartners, you want to integrate them out. We have an effective description in which looks like this kind of theory we are discussing here. So I think there is a motivation to study this kind of setup to discuss gravitino production. Thank you very much for your attention.
Right. So the fact that your energy momentum tensors do not match on your previous slide. Yeah. So what is like the level of
the fact that this T00 for longitudinal gravitino does not match the instantaneous Hamiltonian, this is simple to understand. It's just this time-dependent scaling.
Yeah. So I mean, like, do they coincide in a zero momentum limit, or they're like more severe discrepancy between them? So they do not coincide. So by which you mean like the equations are different, the like formulas are different, or like what is the like magnitude of the discrepancy between them?
I think even in the zero momentum limit, they are on the same interval.
Even in the zero,
I think so.
Well, but if I may say, there's no reason why it should coincide in the zero momentum limit.
It should coincide in the no. We're talking about we're not talking about goldstino. We're talking about instantaneous Hamiltonian versus you're talking about instantaneous Hamiltonian versus the T00 or about the goldstino.
Well, there's like equality sign in between the
This and this.
Yeah, so it doesn't matter.
This should work very well in the high momentum limit, because the equivalence theorem goes in the high momentum limit. Okay.
Okay, right, so.
And it's where gravity is supposed to be subdominant, so the effects.
The equivalence theorem goes for high momentum.
Hmm.
Emilian, there is this kind of approach where people are saying that you can use kind of substitute gravitational field by double of gauge field, double of vector field, right? So if you have this double copy for gravity, then it would be like equivalent to vector theory, right? Essentially, you know, then your no, I mean, 3/2 would be also part of this construction, right? But then it would be similar to what it was for spin 1, right? I mean, if it would be, if you have this double copy in action. No, I'm not sure whether it's applicable to what you said, but it is what people are using. You know, this.
You are talking about the amplitudes, no? You are talking about the amplitudes.
On the flat background.
Yeah, amplitudes, right, yeah.
And as Maxim said, for a flat background, this is a time-dependent background here. So I don't know what is known about this. Nothing probably.
Yeah, no, but for me the signal mostly is about this masses limit. You see, so to the extent that you do not have masses limit, I would expect problem in it all the way, because I mean it could appear maybe in different form, depending what you are talking about. But you already mentioned, right, that there is no masses limit in
Well,
your case.
massless limit would exist if you restore the original degrees of freedom.
Yeah. All right.
Yes. Right.
Okay.
Thank you.
Well, let's thank Emilian again.
Thank you.
So last week we had in somewhat a simpler problem, but second, right? But it was also about
Bye, Arkady.
behavior of the amplitude.
Okay. Bye.
Bye.
Yeah. Nice. I'm sorry if I interrupted too much, but
No.
it was
On the
nice.
contrary, it was very nice. Thanks a lot.
Okay,
Hope to
bye.
see you soon. Bye.
Okay. Bye.
Is Rita Schwinger?
What was last week?
Good point. No, he was saying that RS is Randall Sundgren or Rita Schwinger.
Okay. Yes.
Okay, so then do we
Just like get my